everyone. So in this video I want to look at the concept of reversibility, and reversibility of course relates to literally the idea of processes that are physically reversible, and that can also help us apply it further in the thermodynamic context. In other words, processes that then are thermodynamically reversible. So that's the idea of this example, is just to establish a couple of ideas which are physically reversible, because then we can later on apply them in what is thermodynamic reversibility. Right, so I have some processes for us to look at here. And the first question is whether or not, so we will say whether or not something is a reversible process or not. And the first says, if you expand nitrogen gas into a vacuum, can you reverse that? So let's think about what's happening here, right? So if you have this is a very ugly picture. So you have a little glass test tube, not glass tube, you have two glass bulbs. And the one side contains nitrogen, and the other side is completely a vacuum, right? It doesn't contain anything. And you then open up that valve. So I'm not going to try and redraw that. I'm going to copy that. And you open up this valve. What do you expect to happen, right? Your immediate intuition says, well, you expect the nitrogen to spread out through this little chamber that you have here. But the question is, can you do the reverse of this? In other words, can you force the nitrogen back into the other side? Meaning, and do that, let's say, so can that happen spontaneously? Will that just happen? Just like this happened spontaneously when you open the valve? And the natural answer is no, right? It's not going to happen spontaneously. So this is an example of which is of a process that is not reversible, of a non-reversible process, because once you've opened that stop or that stopper that you had, the vacuum pulls the nitrogen through the chamber, and your nitrogen gas just expanded. And there's actually a very good principle behind this. This is what we call non-reversible work was done by the gas. Not that this is something that we will look at, but meaning that your gas won't spontaneously move back into the chamber as it originally was. So intuitively, this is an example of something that's not reversible. Your gas won't spontaneously just move back to where it was originally. It will remain now spread out through this chamber, and it's not naturally reversible, if we can use that word. All right, so let's look at a couple more of the examples. We're now asked, what about dry ice CO2, which is subliming at 25 degrees Celsius and 1 atmosphere? So in general, phase changes are reversible, right? Because a phase change, when it occurs at the phase change temperature, that's the important part, should be able to, that forms an equilibrium, and an equilibrium is a reversible process. So meaning there's a forward process and there's a reverse process that are occurring at the same rates. In other words, there's something that whatever's the forward can happen in reverse. But what do you notice about this system? It says dry ice is subliming, but at 25 degrees Celsius, the 1 atmosphere is fine, but the 25 degrees Celsius, that is not the sublimating temperature of CO2. The temperature at which CO2 preferably sublimates is much lower than that. So this means this is an example of a non-reversible process, another non-reversible process, not reversible. And it might be easier, so let's first put it in terms of, because what's happening, sublimation is when CO2 solid is directly converted into CO2 vapor. The reverse of this might be easier to understand. When you are at 25 degrees Celsius and 1 atmosphere, right? So 1 atmosphere is at general atmospheric pressure at sea level, and you are at 25 degrees Celsius, which is room temperature. Are you able to form solid CO2, in other words, dry ice? No, right? You're not able to do that. So it's physically impossible to reform dry ice at those conditions. However, if you take a piece of dry ice and put it at 25 degrees and 1 atmosphere, it will spontaneously form the gas form. It will spontaneously form the vapor phase. Right, so in other words, this is an example of a process that spontaneously forms goes into one direction, but you cannot reverse it. In other words, it won't, at these specific conditions, won't be reversible unless you decrease the temperature or change the pressure or do one or the other. You won't be able to form a situation where you can do the forward reaction and the reverse. And that's what's meant by reversible. So meaning you need to find a situation, a setup, a temperature and a pressure and whatever, where both the forward and the reverse is possible at the same time by just doing something to the system. All right, so that is the idea of reversibility. So this is a clear example of, if you take a piece of dry ice and put it next to you on the table, it will sublime. It will completely sublimate from the solid into the vapor phase. But once you have the vapor phase at 25 degrees Celsius and 1 atmosphere, it is impossible to get it back to the solid phase unless you change the conditions, and that defeats the purpose of reversibility, because so it's not reversible at those specific conditions. All right, so now that I've perhaps explained the point a bit better, let's look at C. So it says energy as heat is added to a mixture of ice and water at 0 degrees Celsius, causing some of the ice to melt. All right, so the first question is, what is ice and water? Right, so ice and water, of course, are the, so ice is the solid phase of water, and water is, well, the liquid phase of water. So that should actually say liquid water. And at 0 degrees Celsius, we are indeed at the phase change temperature where solid water will convert to liquid water. So we're told here that energy is added as heat to a mixture of ice water. So that means we have a forward process to go to liquid water. But because we are at the correct temperature for this process, for this phase change, it means that if we just were to remove a bit of heat, this process would easily be able to be reversed, right? We could just remove a bit of heat from the system and then take it back to the solid phase, right? We don't have to change the temperature, we don't have to change the pressure of the system, we can just remove a bit of heat, and then the liquid water would freeze back to the solid phase. And that is the definition of a system that is reversible. Right, and that is clearly different from an example like we had here. Removing a bit of heat from this system wouldn't have sublimated the CO2 back to its solid phase. It would have, removing some heat would have eventually brought it back to the liquid phase and then eventually to the solid phase, but it wouldn't have sublimated it directly. So that does not make it reversible. It makes it, a normal process, not a reversible process. This is reversible because whatever we just did is immediately reversible. Taking a bit of heat from this system here would just condense the gas. It wouldn't make the gas go back into the chamber. So it's also not reversible. All right. And that actually links to your idea of entropy, because the entropy is equal to the reversible amount of heat at a specified temperature. So if you keep the temperature and the pressure constant, it's equal to the amount of reversible heat transferred to the system. All right. So that's why these concepts of reversibility are important. We'll want to look at reversible processes whereby we can transfer some heat in a reversible manner, or in some reversible manner, like for example a phase change at the correct temperature and pressure, and hence then we can determine what the change in the entropy will be for that system. If it's not reversible, then there is something else at play, and you will see what those factors are. And I've already linked it to the discussion of spontaneity. But yeah, sorry, I'm getting a bit ahead of what this example is about. This is just recognizing what is reversible and what is not reversible. All right, so then let's look at the last example. Cool, so the point was here, this was reversible because we were at the phase change temperature and just removing a bit of heat, not changing the temperature, removing heat would have allowed the system to be reversed, right? Or reverse the process. The last example says methanol and ethanol mix forming a homogeneous solution. Now, this is also an example of something that is not reversible. And hopefully you understand the practical implications of mixing two miscible liquids in some ratio and forming a homogeneous solution, because mixing them together means that you won't be able to separate them quite that easily again. You could be able to distill them, but once you've distilled them, then you've technically done some non-reversible, non-reversible work on the system. I've used the word again that you probably don't know, but that's okay. So in this situation, it's practically impossible, right? It's to separate the mixture. And what it basically just means, if you just mix them, there is no way that you can have them spontaneously unmix. In the same way that you can't have this gas bulb or this gas spontaneously go back on the left of this tube here. Your mixture is going to remain mixed. Solutions mix spontaneously, just as your gas expands spontaneously. And that links to the idea of what spontaneity actually is, and how we can link that to the idea of how to predict and how to calculate spontaneity, and what the second law of thermodynamics tells us. All right, so you'll see how the idea of reversibility comes into the second law of thermodynamics. You will see reversible systems linked to the idea of equilibrium, and the second law of thermodynamics, which gives us that at equilibrium, the second law of thermodynamics says the change of the entropy of the universe needs to be zero. Any process that is not reversible is spontaneous and will have an associated positive change with its entropy change of the universe. And we will see that is because of the inherent non-reversibility of the system. because that means there must have been an increase in the entropy of the system, but because of that change, or that positive change in the entropy of the system, it means we physically cannot we cannot make, I'm going to use the word unchange the system. It means we cannot put the pieces back together how they were, because we cannot unmix the mixture of methanol and ethanol. We cannot unsublime this at this specific temperature. We cannot put the gas back in the bulb. We cannot do that because there was a spontaneous change. However, if it's an equilibrium system, we can change because there's a forward and a reverse process. All right, and that's what the idea of reversibility actually tells us. Cool. So this example is a very conceptual idea, and there's a lot of just talk in it, but I think it highlights a couple of nice ideas that we will use later on, that you can think of or think about. Right, so I'll see you in the next video then. Thank you for watching.